just work this problem. So it says a 750 milliliter bottle of Listerine is a 21% weight per volume of ethyl alcohol. All right, now you said your question was specifically on part B.
Yes, because I got part A right, but I couldn't figure out what to do on part B.
All right, well, I'm going to go ahead and work part A really quick for anybody that has not looked at this problem yet. So we have 750 milliliters of Listerine. I'm going to do capital L for Listerine. And the concentration is 21%, and it's volume per volume. So what that indicates is the solute is a liquid and the solution is a liquid. That's all that means. So part A says, what is the volume in milliliters of ethyl alcohol in the bottle? So the solute is the ethyl alcohol. That's the part that I guess cleans your teeth. And then the Listerine is the solution. So ethyl alcohol is the solute. That's what we'll plug in on the top. Listerine is the solution. The volume of that will be plugged in on the bottom. What is the volume? So volume of, I'm just going to write alcohol, EA for ethyl alcohol in Listerine. Okay, so I'm going to stop sharing here and I'm going to go over the iPad and we'll answer part A. Oh, goodness. Okay. Can y'all see this now? All right. So our weight volume percent equation is this. It says, let me zoom in over here, that volume per volume percent is going to be equal to milliliters of solute, okay, which is our ethyl alcohol, divided by milliliters of solution, and I didn't leave space, times 100. Goodness. Times 100. Okay, that's our equation. So we're told that we have 750 milliliters of Listerine. So that's what we'll plug in on the bottom. And it says, what is the volume of ethyl alcohol, which is our solute in this case? Okay. So that's what we're going to plug in on the top. And we're also given the percent, which we could plug in right here. So what we'll say is 21% equals the volume, or actually just write our units, just write milliliters. Milliliters of ethyl alcohol divided by 750 milliliters of our solution, Listerine, times 100. And now we just solve for milliliters ethyl alcohol. So we divide both sides by 100. And then that will cancel. Okay, if it cancels, it goes away. And then we multiply both sides by 750 milliliters of Listerine. And if it cancels again on this side, it goes away. So milliliters of ethyl alcohol will be 750 times 21 divided by 100. And you should get, what did y'all get for that?
I got 157.5 milliliters.
What you got, Danielle?
Yes.
Okay, that's what you should get. So milliliters of ethyl alcohol. So for this to be roughly a 21% solution, 20% of Listerine needs to be ethyl alcohol. So what we just found out is that there's 157 or so milliliters in a 750 milliliter bottle of Listerine. That means the bottle is about 20% alcohol. Okay, does that make sense? Okay, part B is a little more difficult. This is where it gets fun. go back to the desktop. If the density of ethyl alcohol is 0.789 gram per milliliter and the molar mass is 46.07 gram per mole, what is the molarity of ethyl alcohol? What's the concentration of ethyl alcohol in our Listerine bottle? Okay, so I'm going to write a few things down. Density of ethyl alcohol is equal to 0.789, and that is grams of ethyl alcohol per milliliter of ethyl alcohol. Molar mass is 46.07 grams of ethyl alcohol per mole. All right, and we're trying to calculate molarity, so let me go back to the iPad now that we have this info. So what we're solving for is molarity. What is molarity? What's the equation for molarity?
Is it moles of solute over liters of solution?
Mm-hmm. So it's going to be moles. What's our solute here?
Is that what we solved for in part A?
Mm-hmm. Well, is it Listerine or is it ethyl alcohol?
Ethyl alcohol.
Mm-hmm. The alcohol is dissolved in the Listerine, all right? That'd be bad news if they were serving us Listerine dissolved in alcohol. Okay, and calling it Listerine or something else. So alcohol is the smaller portion, right? So that's the solute. So it'd be moles of ethyl alcohol per liter of the Listerine of solution. And so we're trying to solve for this. So do we have any of this information already? We don't have moles of ethyl alcohol. We calculated milliliters of ethyl alcohol, but that's not moles. So I know we're given the percent of the solution, but that's not moles either. If you look at all the information from part A and everything, we don't have moles of ethyl alcohol yet. Do we have liters of Listerine?
Do we just turn the 750 milliliters to the liters?
Absolutely. That's easy, right? So we do have that info, right? We have 750 milliliters of Listerine. That was the first piece of information given to us in the problem. So let's just convert that to liters. Okay, so we have 750 milliliters times, there's 1,000 milliliters for 1 liter. All right, so that just equals 0.75 liters. So we actually have the bottom part, liters of Listerine. So to get molarity, it's asking the molarity, so we have to somehow be able to get moles of ethyl alcohol. So here's what I do have. I'm going to highlight the pieces that I do have. I know that my volume is 157.5 milliliters. That's how much ethyl alcohol is in Listerine. I know that there are, for every 1 milliliter of ethyl alcohol, it's 0.789 grams. And I know that for every 46.07 grams, it's 1 mole. And I need to somehow calculate moles so that I can plug it in right here, divide by my volume, and get molarity. So, any ideas? How can we piece these things together to get moles? We're gonna have to do some converting. We're ultimately trying to convert milliliters and somehow get moles out of it. I'm trying to let y'all think before I just jump in. What could we do? Any ideas from anybody? I'm gonna move this over here so that I just leave myself some space. Any ideas where we should start?
Somebody said something in the chat.
Oh, sorry, my chat is hidden behind my screen. Brooklyn said, convert your grams to moles. Okay, so where do we have grams, Brooklyn? I'm really not disagreeing with you. But where do we have grams? What piece of information gives us grams? Do y'all see grams anywhere? Yeah, density and molar mass, okay? So we know, let's just cancel out grams and see what we get. If we just take 46.07 grams and we know that's per 1 mole, how could we cancel grams? Oh, you're good. What if we multiply by the density? But we need to invert it, right? We need to say the 0.789 grams will go on bottom so that grams cancel, and that's per 1 milliliter. So then we see that grams are going to cancel if we do 46.07 divided by 0.789. And I got 58.4. Or you can write 39. And now what's our units here on this answer? So what units don't cancel?
The milliliter,
Okay, is that it?
and there's moles.
Yeah, so how do I write it?
Milliliters per mole, so with the slash.
Per mole. So what this means is that for every almost 60 milliliters, there's 1 mole of ethyl alcohol. I calculated in my first part that in Listerine, I have 157.5 milliliters. How can I get moles? I need to know how many moles. That's what I need to plug in. Okay, right here. How could we get moles now?
Would we divide, I don't know. Would we divide our moles of the ethyl alcohol or the milliliters of ethyl alcohol by what we just calculated, or?
Yeah, let's take our milliliters that we solved for. We'll move all this up. Okay, and right underneath this, let's take our 157.5 milliliters and let's just convert it to moles. We know for every 58.39 milliliters, it's 1 mole. Well, we have 157.5 milliliters. So we'll just cancel milliliters, convert to moles, right? So for every 58.39 milliliters, that's 1 mole of ethyl alcohol. So do 157.5 divided by 58.39. And I got we'll just say 2.7. And look what happened to milliliters. They cancel and we have units of moles on top. It's not 1 over moles, it's moles, which is good. Okay. So now what can we do? What were we trying to do initially? What was the question asking us? If you reread part B, it says, what is the molarity? Yep, thank you, Autumn. So what should I do?
Plug in the moles and then the liters of our Listerine.
So molarity will be 2.7 moles of ethyl alcohol divided by, what did we saw? We said it was 0.75 liters of our solution, which is our Listerine. So then we just divide it by 0.75. And I got let's say 3.6. Is that what y'all got? Okay, good. So it's a molarity of 3.6 to capital M, which is moles per liter. So in a bottle of Listerine, which is 750 milliliters, there's about 3.6 moles of ethyl alcohol. Or sorry, no, this would be moles per liter. We don't have quite a liter, but the molarity is 3.6 moles per liter. Okay. See how fun that was? We use density, we use molar mass. Just like the whole semester comes together in one problem. Isn't that nice?
Are we gonna have a problem like this?
Do you want one?
I would prefer not.
Yeah, I'm with her.
Really? After we just worked it on recording?
You know, I appreciate
And you would not want a problem like this. What?
I mean, we have no real say. I mean, if it's there, yeah, I'll do it. But
I mean, we just solved it.
I mean, yeah, but on the test, it's going to be different numbers, a little bit different steps in between, and
like
it's a lot to miss. A lot to miss.
If I sat in with an instructor just solving a problem, I'd be like, put that on the exam. Right. Maybe I'm a different breed.
For sure.
Okay. All right. Next problem.
I think this may be a simple problem. Can we do 938 also B? It also has to do with finding moles.
But going back to y'all's question, if there was a problem like this on the exam, I would think now that you know how to convert and you've seen density before, we've seen molar mass, you should have no problem doing one like this, right? Even if I just involved one of those portions. So don't put it past me. All right. Okay, 9.38 you said, Tyler?
Yes, ma'am. On B.
All right, solubility of NH3. 9.3, I don't see a part B. It's just a solubility.
Sorry. So the part A has to do with finding the
I see. I do see a part B. Sorry, I was thinking 51.8 was another part. Okay, the solubility of NH3 gas and water at NH3 pressure of 760 millimeters mercury. Okay, what law is this? I'm just looking at my problem here. Let me share the desktop in case some of you don't have the electronic textbook pulled up. Okay, 9.38. Solubility of ammonia gas in water. So we're talking about the solubility of a gas in a solution. What law did we bring up that talks about solubility of gases in solution? Like the solubility of oxygen in our blood, or the solubility of any gas in a solution.
Is it Henry's law?
Henry's law. This is a Henry's law problem. I think no, it doesn't say that. Just says solution of solubility. Sometimes it'll give a heading that's a little more specific. Okay, so part A, well, let me finish reading the problem. Ammonia gas water at a pressure of 760 millimeters mercury, 25 degrees Celsius is 51.8 gram per 100 milliliters. So this right here is your solubility. So Henry's law is C1 over P1 equals C2 over P2. And just like we did with gas laws, you need to go through and label. So we're given the initial pressure. This is P1. We're given the initial solubility. This is C1. At different temperatures. Solubility of ammonia gas in water at NH3 and 25 degrees Celsius is here. And Oh, they give you the solubility at another temperature. Okay, so maybe that feels complicated because we haven't looked at different temperatures, but they're giving you 2 different solubilities at the same pressure, just at different temperatures. All right, so we'll address that. Part A, what is the solubility of NH3 if its partial pressure is reduced to 225 millimeters mercury? All right. So let me write a few things down. This is 9.38 and P1. So I'm going to write Henry's law. C1 over P1 equals C2 over P2. And I'm just writing down the information the problem gives me. So P1 equals 760 mmHg. And then I'm given another pressure in part A. What is P2?
225.
Mm-hmm. And the units are the same, millimeters of mercury, so we do not have to convert there. And then they give you a C1. This is going to be at 25 degrees Celsius. That equals 51.8 gram per 100 ml. They give you another C1 at 50 degrees Celsius. That is going to be equal to 27 gram per 100 ml. Okay. Let me get over to the iPad and crunch this out. What they should have done is given you, I think this question's poorly worded. They should have said, what is the solubility at 25 degrees and what is the new solubility at 50 degrees? Okay, so they've given you 2 C1 values because they're different depending on what the temperature is. Okay, remember that solubility of gases, as you increase temperature, the solubility of a gas decreases. Gases are most soluble in liquids when it's cold. Gases are least soluble in liquids when it's hot. Okay. So we're trying to solve, the piece we're trying to solve for, what is the solubility? We're solving for C2, but we have to do it twice. They don't tell you that. They want you to solve for the C2 at 25 degrees and they want you to solve for the new C2 at 50 degrees, but we'll work it the exact same way. So part A says, what is the solubility at the new pressure, 225 millimeters mercury? So let's just plug all this stuff in, solve for C2. Actually, I'm going to rearrange my equation real quick. So we'll multiply both sides by P2.
For part A, all I did was I did the calculation for the first temperature, and then it's the right answer, but I think it uses the second temperature, which I may be wrong.
For part B?
Yes, ma'am.
Okay, we'll look at that. All right, so C2 is going to be equal to P2 times C1 over P1. All right. Okay, so we'll just plug everything in. P2 is 225 times the C1, which is, this is going to be the at 25 degrees Celsius part. So we'll plug in 51.8 gram per 100 ml. Remember, you do not divide by the 100. 100 is part of the units here. Divide that by P1, which is 760 millimeters Hg. That will give you C2 at 25 degrees Celsius. We do it again at 50 degrees Celsius. It's the same equation. This time we're going to use this value for C1. So same pressures. But this time we're using 27, not 25, 27 gram per 100 ml divided by 760. Okay, you see how it's the exact same equation? Just because we're at different temperatures, the solubility of the gas has changed. So we're just plugging in we're just plugging in each C1 depending on what temperature we're using. Pressure ratio is the same. All right, anybody have the answers for C2? What's the one at 25 degrees? What'd you get, Tyler? Maybe you already solved them, you said.
First one is 15.3 grams
Mhm.
per 100.
And that's going to be grams. Gram per 100 ml. And what was the next one? Pressure has decreased, so solubility should decrease because they're proportional. As pressure decreases, solubility decreases. As pressure increases, solubility increases. That's all Henry's law.
I got 8 grams.
Okay. Don't let me know if you get something different. That's what Danielle got. Okay, part B says how many moles of NH3 would be released from 1 liter of a saturated NH3 solution? The temperature increased from 25 to 50. Okay. This is part B of 9.38. Tyler, here's what I'm going to tell you. I'm not going to put something like this on the exam.
Thank God.
For sure, because I had trouble on this one too.
I promise. I would put something like Listerine on the exam.
Okay.
Okay? Because you should be familiar with density and you should be familiar with molar mass. All right? And we know how to do conversions. We've had to do this all semester. But do you know how many people would be tripped up on a problem like this?
I think I tried for like 25 minutes and I just moved on. I just couldn't do it anymore.
Okay. Well, I would love to solve it for you, but I think it would be a waste of our time because you know what? It's not going to be on the exam. It's not going to be on the final. It's a clever problem. You have to calculate a ratio. You have to get molarity and solve for moles, and you can get molarity because you have gram per 100 ml. You can convert to moles over liters, knowing the molar mass of NH3, which we could calculate, and then you get a ratio there. But I'm not going to spend the time to do it because I can promise you it's not going to be on the exam. Now, if you did spend time working, I don't think that was wasted time because you're making your brain think. But yeah, don't worry about it. Okay. Autumn has a question for us though. But we did work a Henry's Law problem, okay, which will be on the exam. Definitely expect a Henry's Law problem. I'll give you 3 of the 4 pieces. You solve for the 4th one, okay? Any questions on Henry's Law? The biggest thing is you've got to make sure units of pressure are the same. So like if I said P1 was 0.5 atm or 30 psi, and P2 is, 500 millimeters mercury, that's an issue. You've got to convert and get units of pressure the same before you plug in, okay? Units of concentration are always gram per 100 ml. Autumn said, can we do the last problem on chapter 10 homework? Absolutely. I keep getting 16, and that's not an answer choice, sadly. Okay. Yep, chapter 10 homework, here we come. And then we'll continue focusing on chapter 9. Am I sharing my screen with you guys? Can y'all see? Just go to the course home. Let me get all the way there, and then I'll chapter 10 homework. So he says the very last one, Autumn. So that looks like question 95. Chapter 10, question 95, is that the right one? And it says, how many milliliters of a point something molar solution of H2SO4 are needed to neutralize? Okay, now I can share my screen to it because I have it pulled up. Okay, this one right here.
I think she said hers is 87. That's what it is on mine too.
Oh, so this is not the right one?
Yeah.
Oh no, you're on the second to last problem.
Autumn, you're breaking up. I think you're gonna have to type us in the chat. What'd you say, Tyler?
You're on the second to last problem.
Oh, she did type us in the chat. I'm just not reading. Oh, okay. Let me go back one. Hey, so that's not it. Oh, I'm on 25 out of 26. Here it is. This one? All right. How many milliliters of a 0.1 molar NaOH solution are needed to neutralize 24 mils? Okay, you know what's interesting? This is actually chapter 9 stuff, but we say it's chapter 10 because it's acid base. So this is a 3-part problem from chapter 9. So it's kind of combining both concepts. So if I were you, I would actually, anytime it says you've got 2 different substances here, it's NaOH and HCl. Anytime it gives you information on one thing, so you're given molarity of NaOH, and then you're given volume and molarity of HCl, and then it asks you about a volume for NaOH. So let me go back. I'm going to go find the slide on our solutions lecture where we talked about. It's right here. Here it is. Why isn't it? Where is my life? Sorry, it's not connecting. This is one part about being in person that I'm not gonna miss. All these freaking screens. Okay, come on, and here it is. Okay, this is the slide that I'm thinking of. So this is from our solutions lecture. This is chapter 9, and you see the name of that lecture right there. And we're using molarity here in a problem that's involving stoichiometry, which I didn't use this whole word a whole lot because sometimes that word freaks people out, but stoichiometry is just conversions between moles and mass. Here it's between moles and volume using molarity, okay? Autumn says I use M1V. Okay, yeah, you can't use M1V1 equals M2V2. Here's why. You have to use a mole to mole ratio, okay? So let's look at this and your titration problems that you do in lab this week. So we're going to be, if you've looked at the lab procedure at all, that lab procedure walks you through how to do a titration problem. And that is the exact same thing like we're about to do here. So what we're going to do here, know that you're going to use it to answer problems on your lab this week. Exact same method. And you've got to use, I'm going to highlight it. You've got to use a mole ratio as the middle part, okay? Or you might not get the right answer on these problems, okay? So let me read the problem. It says we have this. We have 0.1 molar NaOH. Says your numbers may be different, Autumn, on your problem. And then it tells me on my problem, I've got 24 milliliters, and I have a 0.15 molar solution of HCl, okay? So if your numbers are slightly different, you just plug in your numbers. All right, so here's what we're gonna do. Okay, balanced reaction, that's the first thing we need. So let's write a balanced reaction. I'm gonna zoom in and do it right over here. NaOH and HCl, what's gonna happen? You got a strong base and a strong acid here, so I'm just gonna draw a single arrow because this will go to completion. What products do y'all think we'll get?
For some reason, sorry, go ahead.
No, go ahead, Tyler.
For some reason, I want to say we're going to get, I don't know, NaCl and then H2O.
Oh, that's perfect.
Okay.
Okay, because this and this are going to combine. And then the NaOH and the Cl are going to combine. It's kind of like a double displacement reaction. Not kind of like, it is a double displacement reaction. But it's also acid base. All right, let's continue. Now that we have our balanced reaction, is it balanced? Coefficients of 1? Yeah, it's balanced. coefficients of 1. So you're going to be tempted, even though the mole to mole ratio is a 1-to-1 here, to skip it, and don't, because it affects your units. Numerically, you should get the same answer, but it won't affect your units, or will affect your units. So here's what it says. It says start with what you're given, the volume of solution A. So for which of these things do we have the volume given to us? NaOH or HCl?
HCl.
HCl, we're given the volume right here. All right, so I have 24 milliliters, and I need to convert this to liters. So first thing I'm gonna do is convert it to liters. And you should get 0.024 liters. Okay. Second thing we're going to do once we get liters is we're going to use molarity as a conversion factor. So what is our molarity for this particular problem? We're given 2 molarities. We're given the molarity of NaOH, but that's not what we're using right now because we're focusing on HCl. We started with the volume of HCl. We're going to get moles of HCl. And to do that, we're going to use molarity to convert. So I have 0.024 liters, and I want to convert to moles of the same substance I started talking about, which is HCl. So we know, if I zoom in on molarity, we know units of molarity are moles per liter, right? That's what molarity is, moles per liter. So you could easily rewrite this as 0.15 moles per 1 liter. I always encourage you to do that because it'll help you see how you need to write it. Over here, when I convert, I'm going to put 1 liter on bottom and 0.15 moles on top. My computer is about to die. Okay, so what do y'all get for liters will cancel? What do we get? 0.024 times 0.15. .036. Okay, so that's how many moles of HCl. Now we do our mole to mole ratio. Okay, so I have that was technically we consider this step 1. Now we're going to do step 2, but we have a step before step 1, which is write the balance reaction and convert milliliters to liters. So step 2 is we're going to say, okay, we got 0.15 moles of HCl. And based on my balance reaction that we wrote, for every 1 mole of HCl, it's 1 mole of NaOH, okay? Moles of HCl cancel out, and we should get 0.15 moles NaOH. Again, don't skip that step. The numbers are the same, right? 0.15 and 0.15. Wait. I'm sorry, y'all should have stopped me. It's 0.36, right? 0.036. I just didn't even, I ignored what y'all told me in the chat, sorry.
I'll put that into y'all's calculator because I did that and I may mess it up, but it gave me 0.0036. So I don't know.
What? 0.024 times 0.15?
Yes, ma'am.
Yeah, that's what it should be. Thank you, Tyler.
Oh yeah, I see. I left out a 0 when I was putting it in.
Okay. I thought I was losing my mind.
Well, if you haven't learned by now, you should always do chemistry in pencil, not in pen. See, we'll erase a lot. So it should be 0.00. So Autumn, that may be one thing you're missing when you work this problem. That may have affected your answer. You did this so wrong. Not even close. Okay. And then step 3. All right. We're going to use the molarity of NaOH and convert to volume. So what was the molarity? The problem gave that to us. It's 0.1 molar. This is what I wrote off of the Mastering Chemistry assignment, what I'm looking at on my screen. So 0.1 molar. Molarity is 0.1 molar, which is what? 0.1 moles of NaOH per 1 liter. That's what molarity is. So now we're going to use that to convert from moles to a volume, liters. So 0.0036 moles. And for every 0.1 moles, it's 1 liter. So divide this by 0.1, and then you get 0.036. And on Mastering Chemistry, the only options it gives you are milliliters. Right now, we have units of liters. So moles cancel. So we'll just convert this back to milliliters. So for every 1 liter, it's 1,000 milliliters, and you should get 36 milliliters. Normally in class, you would see me work this out without stopping and like getting my answer every step of the way. You would just see me do one continuous thing. So it might feel like several more steps because of that. But usually I just write it without pausing and getting the answers, and we calculate everything in one big giant thing in the end. So Autumn, when you plug in your numbers, do you get your answer as an option now? They work out? Okay. Oh, we had the same numbers. Beautiful.
Can I ask a question real quick?
Yeah, absolutely.
So for some reason I got lost when we got to multiplying our molarity or our moles for NaOH by the 1 liter over our 0.1 mole. Is that just multiplying it by molarity and then flipping it, or?
This right here is the molarity, the 0.1 molar. So we said, okay, the problem tells us we have 0.1 molar NaOH, and I just rewrote it with units of mole per liter because I realized what I need to do is I'm using molarity as a conversion factor. So I'm trying to cancel one unit and convert to the other. So I'm either trying to cancel moles and convert to liters, or I'm trying to cancel liters and convert to moles. Here, I'm given moles of NaOH, and I'm asked to find the volume. All right, if I'm reading my Mastering Chemistry problem, it says how many milliliters, which I know is a volume. So I'm trying to cancel moles and convert to liters. So that's why I inverted it and plugged the moles in on bottom.
Okay.
Yeah, but it's still plugging in molarity as a conversion
Sweet.
factor.
Thank you.
Yeah.
For some reason, I thought for a second that we would use, even though we're using moles as a conversion factor, I thought of the molarity equation, and I thought of plugging that in. But
What do you mean? What equation?
which it wouldn't make sense because we're not working with. I guess it would. The molarity, where it's molarity equals the moles divided by liters.
Yeah, that's what we did. This is molarity.
Oh, okay. I guess when I did in my calculator, I did the opposite. I did 0.1 divided
by 1.
Divided by the 0.0036. But that I think.
Well, so what we're doing is we're given molarity 0.1 molar, and we know how many moles. We're trying to find the volume. So you could plug in 0.0036 mole and say, okay, then what is my volume? You could do that. But what do you end up doing? You got to rearrange and solve for volume, right?
Yeah.
So this is volume. So I got to multiply both sides by my volume. I'm trying to isolate volume.
Oh, I see what I did. I thought I could divide. I need to learn. I thought I could divide the moles.
And then you divide by 0.1 on both sides. Volume cancels. So you still end up doing 0.0036 divided by 0.1, which is exactly what we did over here.
Sweet.
Either way, Tyler.
I think I just messed up. I tried to divide the moles, and the volume was still the denominator. So
Oh, okay.
yeah.
Autumn said, I struggle with knowing what formula to use because since there was no V2, that's why I use M1 V1 equals V2. Yes, this is the classic thing people try to do. They try to use a dilution equation to solve molarity in stoichiometry problems. Okay. Now, if you're technically you want to know the truth, if your mole ratio right here, if that is a 1-to-1 mole ratio, numerically you'll get the same value. It's just you haven't worked it out to see all the units, okay? So the moment that you try to work a problem like this using M1V1 equals M2V2, and the moment your mole to mole ratio is like a 1-to-2 or a 2-to-3 or a 3-to-1, you'll miss it every time. That equation, I could break it down and show you how you are multiplying a molarity and a volume, and so it kind of makes sense in some regard, but the moment that your mole ratio isn't 1-to-1, you will never get the right answer. So that's why you have to learn how to do it this way, because you have a balanced reaction, and you have to convert at some point from HCl to NaOH, and you can only do that with a mole to mole ratio. All right. That's a great question. So there's a lot of equations, right, between chapters 9 and 10. And honestly, if I were you, I would kind of make a sheet where I have all my equations. Would y'all like to do that real quick? Write out all the different equations? Would that be helpful? I'm happy to work more problems as well. We got about 10 minutes left. So I'm just going to go to a blank slide here. Equations. Oh, let me see if I can think of everything. So we started with solutions. I'm actually going to just scroll through. I'm sorry, I hate scrolling this much because I know it's hard for y'all to like watch. Well, here's two equations, weight, volume, percent, and molarity. Okay, so we got weight, volume, percent, or like with the Listerine problem, it could be a volume per volume, but it's the same equation, meaning that you have grams of your solute. If it was volume per volume, it's just milliliters of solute per milliliters of solution times 100. We have equation for molarity, which is just a capital M, and that is moles of solute per liter of solution, and no times 100 there. We have Henry's law, which is C1 over P1 equals C2 over P2. And this is when you're talking about the solubility of a gas in a solution. So if I was like, you have some sort of carbonated drink, that's a gas dissolved in a liquid. Or the solubility of oxygen in the blood is blah, blah, blah. That's a gas in a solution, which there is your blood. What else do we have? We have dilution, which is M1V1 equals M2V2. So M being molarity, mole per liter, volume. As long as V1 and V2 are the same, you can use milliliters or liters. Okay, we'll work 9.48. Yeah, Tyler, thanks. If we keep going, we have, you need to know how to calculate an equivalent, right? We talked about equivalents and milli-equivalents. We don't really have, I don't know if we really have an equation for that. We have a definition for what that is. Electrolytes, remember how to determine or distinguish between strong, weak, and non-electrolytes. But here's where we talked about equivalence. We're looking at the number of ions that carry 1 mole of charge. Okay, so the number of ions that carry 1 mole of charge. So what's really important to us is not the identity of the ion, it's the associated charge on the ion. Okay, so that is E lowercase q is equivalence equals number of moles of ions that carry 1 mole of charge. Okay. We talked about osmolarity. And we said osmoles, so that's the number of moles of particles. Here we don't care about the charge. We just say, okay, how many particles do we have in solution total? Per liter of solution. And what else did we have? Do we have anything else? After, so there's examples where we're calculating equivalence on these things. We skipped over colligative properties. We talked about osmosis. Yeah, number of moles of particle per liter of solution. And then the vocabulary words that go with that. So knowing between isotonic, hypotonic, and hypertonic. All right. Know the difference between those things. If I had you calculate osmolarity for a couple different solutions, and then ask you which one is, hypertonic or hypotonic, or are these solutions isotonic, I could ask you questions like that. All right, that should be it for chapter 9. Chapter 10, we have a lot, and some of you, we haven't even gotten to some of the things we're going to cover. We have Ka for weak acids, which is the concentration of H plus or H3O plus times the conjugate base over the concentration of HA. We're actually going to solve a problem today where we calculate pH from a weak acid solution. We're going to get to this, so if your lecture is at 10:50, just hang tight. But this equation will have pH is the negative log of the concentration of H plus. POH equals the negative log, of the concentration of OH minus. Oh, one that I forgot. Hold on, one more real quick. pH plus POH. This is all stuff we'll talk about in lecture day equals 14. So we're going to talk about the pH scale. KW equals the concentration of H plus or H3O plus times the concentration of OH minus. So if we know KW, and if we knew the concentration of H plus or H minus, we could solve for the other. We'll go a little past 10:30 today. We'll work problem 9.48. And then we'll have one more big one when it gets to buffers. We'll have our Henderson-Hasselbalch equation. So again, hang tight. We'll get to this equation in lecture day, but it equals pKa plus the log of the conjugate base over the concentration of the weak acid.
What does pH plus POH mean or equal?
14.
Okay, I just wanted to make sure.
Yeah, it's a 14. So these are all the equations. So when you work a problem or you read a problem on the exam, seriously, come to a sheet like this. Okay, am I given molarity? Is this telling me about like a concentration and pressure? Just kind of see what variables you have in your problem, and that should allude you to or direct you to what equation to use. And then sometimes, the problem might say, you have this solution and you dilute it to blah, blah, blah. And if it had that word in there, like you're diluting it, that would be, okay, I'm going to use a dilution equation. So sometimes there might be keywords that can help you decide what equation to use. All right, Tyler wants to look at 9.48 from the textbook. Oh, why am I trying? I have it right here, 9.48. Here it is. Okay, what the question says this. Sorry, some of y'all may still be writing. What is the mass volume percent concentration of the following solutions? Oh, this is great. For sure, expect stuff like this on the exam. Okay. If you need me to come back to this in a second, I will, but 9.48 from the textbook. What is the mass volume percent concentration? So we're solving for mass volume percent. So what's our equation for mass volume percent? We just wrote it up earlier. It's grams solute per milliliter of solution times 100. And for part A, you are given the following info. It says you have 0.078 moles of KCl, and you have 75 milliliters of solution. What should we do? We're given moles. This is our solute right here. We're given moles, but we need grams of solute. So how do we go from moles to grams?
You have to convert
I'm gonna
use
fall
the
out of my seat if nobody can tell me what to do. Okay, thank you, Danielle. You got to convert it from moles to grams. How do we do that? Using a what?
So we use the mole to mole or molar mass or something like that.
Molar mass. All right, KCl. What is the molar mass of KCl? We need a periodic table to calculate this. Periodic table. I have one. Here it is. Where'd it go? Okay. It's on my desktop.
I got 74.548.
For the whole thing?
Hmm.
Yeah, K is 39.1 and CL is 35.45. So you add all that up and you said you got what, Tyler?
74.55.
Yep. All right, so we're going to take this 0.078 moles of KCl and convert to grams, because that is what we're going to plug into our mass volume percent equation. So for every 1 mole, it is 74.55 grams of KCl. What do we get here?
5.8.
All right, 5.8 grams. I'll leave it there. I'm out of room. Oh no. Okay, we'll make do. And then I'm given 75 milliliter solution, so I'm literally just going to plug that in right there into our equation. So mass volume percent, I guess I'll do it down here. I'll squeeze it in. Mass volume percent equals 5.8 grams of KCl divided by, we don't even have to convert our milliliters. It's just we plug in the 75 milliliters times 100.
Can you scroll down some?
Can you see? I won't let me scroll down anymore. It's like the bottom of the sheet.
Okay.
Could I add another sheet? How do I add? Add a sheet. I don't see that. It only gives me like 3 pages on a blank note. I could zoom in. Does that help, Danielle?
Yes.
So Autumn, you said you got 7.73%. Once you multiply by 100. Okay. And then the very last one, this is all we'll have time for. Sucrose says, so I need a new note now. This is a 9.48 part B. It says you have 0.044 moles of sucrose, which is C12H22O11, and you have 380 milliliters of solution. Same exact thing here. Use molar mass of sucrose and convert. I don't want to calculate this. It's 342.3 grams per mole. So we're going to take the 0.044 moles of sucrose. Convert to 1 mole. And that is going to be equal to what? A very small number of grams. What did I do?
I got
I'm
15.
I'm crazy. I did it wrong. It's 1 mole times 342.3 grams. Sorry, we're trying to cancel moles here. Even I make mistakes. All right, well, you got 15, Tyler?
Yes, ma'am.
Autumn, I messed up. I put grams on bottom, moles on top. That's what I did wrong. I'm trying to cancel moles, so moles need to go on bottom. All right, and then you plug it into your mass volume percent equation. So 15.06 grams of solute divided by, we're already given the milliliter solution, 380 milliliters of solution times 100. And you should get, yep, 3.96% sucrose. Okay. There it is. So we did examples of mass volume percent. We used molarity and did a 3-part problem. We did a Henry's Law problem. We did that fun Listerine problem. So we worked a lot. I hope that was helpful. You guys feel okay, at least now? Here's what I think you need to focus on for chapter 9 after this. You need to spend some time looking at equivalence. Okay, so like if I'm pretty sure there's some example problems in the textbook as well. But if I say you have a 0.5 molar solution of, KCl or NaCl or whatever, how many equivalents is this? Calculating that. And then if I were to tell you, you have a 0.75 molar solution of glucose, what's the osmolarity? Questions like this, all right? If you have, there's practice problems. You could rework some problems on the homework chapter 9 that I know had you do stuff like that. But spend some time making sure you understand osmolarity and if something is isotonic or hypertonic or hypo compared to another solution, and equivalence. And then also determining like if a particular solute would be soluble in a given solvent. So like dissolves like, polar versus nonpolar, and when something would be soluble or not soluble. And then the last thing is look over the solubility graphs that we talked about and know how to read one, in case I put one on the exam and I say, what's the solubility of, glucose or sodium chloride or something, in solution, or what would be the solubility? I could do it with gases too, because we talked about solids dissolved in liquids and gases dissolved in liquids. So, hey, I got 10 minutes before my next lecture, and some of y'all need to take a little mental break anyways. Thanks for joining. This will be posted later, okay?